So we do have a little bit of a problem with using a microcontroller to control the gate voltage of our MOSFET. And the biggest issue is that this microcontroller doesn't have an analog output. And also the gate voltage required here, at least in our situation here, is about 12 volts. And this microcontroller can output 3.3 volts. So we've got two issues. 3.3 volts, no analog out. There we go. So to solve these two issues, what we're going to do is use an amplifier for this to get our 3.3 volts up to the 12 volt gate voltage that our MOSFET requires. For the analog output, it gets a little complicated. One of the things that these little microcontrollers have is they have something called PWM. And what PWM is I can have a frequency and a duty cycle. So I can program one of the pins of the microcontroller to output a waveform on a frequency, so just a waveform like this. So it could be cycling 1,000 times a second, it could be cycling 20,000 times a second, it could be cycling 1,000,000 times a second, all the way up to in the megahertz range. It's just limited by the frequency of the CPU in here, which is quite high. So I've got a lot of flexibility around that. But so I can have a particular frequency, but then I can also have a duty cycle. So a 50% duty cycle here would be, this is only going to be on 50% of that cycle, the up part right here. So this would be an example of a 50% duty cycle. Or a 25% duty cycle that would be even like a little thinner guy like this. So you get the idea. With PWM, I can program one of these pins to do this. Now, this doesn't give us an analog output, but it does kind of control the amount of energy that's coming out of this pin in a sort of average way. So if we run something like this into a filter that smooths this and averages it out, what we can do is we can get that to look like a 3.3 volt divided by 2. This one can look like a 3.3 volt divided by 4. This one can look like a 3.3 volt divided by 8. But we have to smooth this. And to smooth this, what we do is we run it through an RC filter. And this is, R is for resistor, C is for capacitor. We run it through a, basically we take the signal in, we run it through a resistor, and then we shunt it through a capacitor to ground. And so then we can take the voltage across here, and this then becomes our smooth analog level. So what we can do by varying this duty cycle between 1, and actually I forgot the duty cycle that's 1, a duty cycle 1 is just a single 3.3 volt like that. Duty cycle 1 all the way down to fractional values, we can vary the analog output of this RC circuit between 0 to 3.3 volts. And then in combination with this amplifier, we can step this 3.3 volts up to 12 volts. So in this way, with this combination of an amplifier, PWM, and an RC smoothing circuit, we can get this tiny little Raspberry Pi Pico to output the analog 12 volt gate voltage we need to modulate the output of this thing and drive it dynamically to target a particular voltage drop. Okay, so here's the circuit on a breadboard, and it looks probably a little bit more complicated than it is. I've done my best to clean it up, but it's hard on a breadboard, and I'm going to try and walk you through it. We've got a bench power supply over here providing 12 volts, roughly 12 volts down here, and to this side of the breadboard. The Raspberry Pi Pico, which is the microcontroller, is powered via USB, and that's a 5 volt power supply. So there are two power planes here, a 12 volt power plane and a 5 volt power plane, and it's very, very important that there are two grounds be wired together, and that's this little pin right here. Those two tie the ground planes together. It's very important if you're using two different power supplies in a circuit, you must tie their grounds together. The Raspberry Pi Pico has an input and an output here, basically. The input is ADC0, which is, I believe, GPIO 29, and that's over here, and this is reading the actual voltage across our load. So this is our Chinese load simulator with a little cool user interface where we can dial up a particular amperage load and it will tell us the voltage and the power that's going across. It's not doing anything right now, it's not drawing any amps. But what we do is we have a little voltage divider over here that measures the voltage between here and divides it by 4. And that's what this analog pin is sensing. So this allows the code on the Raspberry Pi Pico to sense the voltage across this load. So it's dividing it by 4, so currently showing about 5 volts. So this analog pin should register about 5 divided by 4 volts, or what is that, 1.25? The next thing that we need to do is relatively complicated. Remember, in the past, we had this guy wired up, and he can take 12 volts across it, and you can spin the little knob, and the output varies between 0 and 12 volts. That's wonderful. Well, the Raspberry Pi Pico can output between 0 and 3.3 volts. So you can see here we've got a resistor and a capacitor to ground, and that means that when I pick up the voltage here, this is a smoothly varying between 0 and 3.3 volts. Now, unfortunately, our MOSFET requires up to 12 volts on its gate. 3.3 volts just isn't going to cut it. So what we wired here is an amplification circuit. And this amplification circuit is called an op-amp. And it's got a voltage divider here that tells this op-amp to multiply the input voltage coming in here by 4 to the output voltage. So here, this goes to the gate of our MOSFET. So that allows our Raspberry Pi Pico to sense the voltage across the load and to vary the voltage across the gate. But we need to write some software that controls that feedback loop. Okay, so what we need to do is write what's called a PID controller. And it's a little hard to describe exactly what a PID controller is, so I'll use a little bit of a metaphor. When you have a shock and spring system on your car, PID controller performs, so the shocks and springs on your car are designed to allow your wheels to adapt dynamically to the road surface and modulate your suspension in such a way that it always has a controlled motion. It responds dynamically, but brings the wheels back into alignment in a controlled way. And so PID controller, P stands for proportional, the I stands for integral, and the D stands for derivative. And the P is a little bit like the spring. So it says, I'm looking at a target. So for example, I want my suspension to always be in the middle. So that's my target. If I look at how far away my wheel is from the target location, that's how strongly I want to push it back. And springs do exactly that. The more you can press them, the more they push back. So the P in a proportion PID control system is the drive to go towards the target effectively. D is like a shock absorber, so like a pneumatic shock absorber. Those provide damping. So the faster you go towards that target, they'll slow you down. So even if you're going away from the target or towards the target, they'll slow you down. And then the integral component is like an adaptive suspension. So it notices that maybe your ride height is a little bit too low, and it slowly adapts to get you back up to that target. And the end result would be a nice controlled suspension where your wheels are always dynamically seeking the right position for the road surface and the ride height, right? So the PID controller does that with a target and a control signal that it can do. So what our target will be is the target voltage across the load that we want. The microcontroller gets an input of the measured voltage across that load, although it's a fraction of that, so it has to multiply it back up. And we also have the issue that the resistors that we're using aren't terribly accurate. so the voltage divider isn't exactly dividing by 4. So we'll have to adapt for that a little bit. But anyway, it can read the voltage across the load, and then it can control the PWM modulation to control the voltage across the gate of the MOSFET. So basically it can read the voltage and twiddle the effective equivalent of our potentiometer knob to target a particular voltage. And so you can see the PID controller logic that we have up here. There's a little bit of math to calculate the derivative, the error, and the integral. And we have some tuning knobs that we can do. And I don't want to get into tuning a PID controller. I spent a lot of time twiddling around with this. There's all sorts of theory and black magic about it. If anybody tells you they do anything other than just guess at PID parameters until they get something that works well, they're probably lying, or they've written a PhD on the topic. But anyway, these values work. So if you look at this, this says that it has a very, very strong response to the error. So if our measured voltage is far away from the target voltage, we will adjust strongly with our output signal in the right direction to get our measured voltage up to the target voltage. The integral factor is much smaller, but this says if there's a persistent error over time, we'll start to drift towards it. And then we have some damping. And what that damping does is it tends to prevent oscillations. If you don't have the damping, what you can have is a system that will kind of overshoot the voltage and then go, oh no, I'm over, now I have to come back down, and then undershoot and overshoot and undershoot, and you get oscillation. So that's the PID controller. And it outputs a number between 0 and 10, which is just basically a 0 and 100% duty cycle. And then we get into the meat of our algorithm here. We specify our target voltage. We specify the ADC input, so we're reading pin 26. ADC input 0, that's what we read. We use a PWM frequency. Remember, the PWM is a oscillating frequency, and the base frequency is 50,000 hertz. And then we vary the duty cycle, and that's what gives us our gate voltage. We're going to be constantly changing this duty cycle on pin 15 as we measure our voltage on pin 26. And then we have some math to calculate the PWM, this wrap thing. I don't know. They do some odd math in terms of how they control the PWM, and it has to be relative to the CPU frequency as well, but we can ignore all that right now. Basically, we're just setting up that PWM output. The next part here is that we take 3 samples of our ADC input. So we read it, and then we do this exponential decay function. So every time we read it, we blend it in with the old one. So this is kind of a trick I learned a while ago. Alpha is typically a small number, so here alpha is 0.01. So every time we read a new value in, we say the new value is 1 minus alpha, so that's about 99% of the old value, plus about 1% of the new value. So we do this running average, and what this tends to do is average through noise very well. It does slow down the signal quite a lot. If the input value changes rapidly, this will slow it down. You will not see it, but this is running very, very quickly. We're doing 3 almost instantaneous measurements of the analog input, and then we sleep for 10 milliseconds here so that we're not, just pounding things. So basically, we're taking a measurement 100 times a second, and then we do our calculations, set our PWM, and see what happens, and then loop again. Now here we calculate the voltage, so it's going to be, remember, 4 times the ADC input. Remember, we had the voltage divider that divides by 4. And why is that? Well, because the voltage across this load could potentially be up to 12 volts. And our analog input can only measure up to 3 volts. So we've got to divide it by 4. That's no problem because we can just multiply it by 4 back out here again. I do have a correction factor. It's about 5% off, and that actually correlates pretty well with the inaccuracy of the resistors that I'm using here. And then here is the main guts of the loop. So we're getting our PWM output from our PID controller algorithm, and we give it our actual measured voltage and our target voltage, and it basically says, okay, this is what you should set the MOSFET voltage to best to achieve that target. and then we set the PWM channel level to that value, doing a little bit of math here. And then we also have a count, so we can output every 25 loops here, and so that should give us, I think, about 4 times a second this is going to output something. And so let's click over to that window and see what's happening here. So we can see the gate PWM is about 60%. So that duty cycle on the PWM is about 60%. And then it has the measured voltage and the error here. And so now what I'm going to do is I'm going to introduce a little bit of a load. And you can see here, if you've been watching this flicks a little bit. The accuracy of the voltage measurement here isn't great. And it also seems like there's a little bit of odd granularity, like it can only do the 4.93 and the 5.01. There isn't anything in between. So now what I'm going to do is I'm going to try and get back up to our 250 milliamp load and see what happens. We're going to call that close enough, 0.24. Now you can see that the gate PWM adjusted dynamically, but throughout that entire sequence, the voltage did not vary. So the PID controller is doing its job of dynamically adjusting the gate voltage. As you can see, the gate voltage went up a little bit to hit those targets. And now I can very quickly vary the load here. So let's spin up actually a relatively high load, and you can see that the gate adjusts automatically, as does the gate voltage. I turn it back down again. We can see the gate closes down a little bit. And we can actually support relatively high loads here. Our MOSFET is now, this entire circuit is dissipating about 10 watts, and you can see here that our synthetic load is dissipating about 4 watts. So the MOSFET is dissipating about 6 watts right now, which it's perfectly capable of doing because I've very jankily strapped it to this aluminum ruler here, this aluminum square. It would burn up if it weren't attached to that. And actually, I don't want to run it that high of a load for too long. But you can see whatever load I dial in here, this PID controller loop running on the MCU does an amazing job of very, very quickly adjusting the gate voltage. So it's actually a relatively handy little circuit. It's a linear regulator. I've rebuilt a linear regulator, one of the most common sorts of power supplies you'll find in electronics. A very, very reliable, but incredibly inefficient way of doing things. Let's turn this back up again and do a little bit of math here. 0.25 amps or 250 milliamps. The load says that we're dissipating 1.3 watts right now, roughly. The bench power supply says that we are outputting a total of about 3 watts. So if we do the math on that, that's 1.3 divided by 3. We're about 43% efficient. That's not great. We're wasting a lot of energy in that MOSFET. For that 1.3 watts that we're sinking into our load, we have 3.2 minus about 2 watts that we're losing in the MOSFET. So it's not very efficient. It's not a great way to do this. And again, you're not going to be wanting to be sinking multiple watts, 3 to 5 watts or 15 watts of energy into just a normal PCB without some serious heat management considerations put into the design, some sort of a heat sink or better ways of spreading that heat around the board. We're still wasting a lot of electricity, about the same as we were previously. So are there better ways to do this? Yes, there are. The next step that we want to take is we want to upgrade this circuit to be a switched mode power supply. And what we're going to start with is a simple buck converter with a diode. Oh, one thing that I didn't talk about is that you can very, very easily have this circuit target a different voltage. So here, if I want it to do 3.3 volts, I can go ahead and run it. You can see on the serial output from the microcontroller, we're getting 3.3 volts exactly. Our gate is open less because we have to drive less gate voltage to be able to achieve that level of voltage across our load. As we up our amperage on the load, we see that it's got very, very good control. We successfully created a linear regulator combining a Raspberry Pi Pico with a MOSFET and some other passive components. In our next video, what we're going to do is we're going to adapt this. We're going to use the same Raspberry Pi Pico to create a control loop, but we're going to get a bit more sophisticated and create a switched mode power supply. And in this mode, what we do is we actually use the MOSFET to switch current at relatively high levels. This results in a much more efficient power converter, but it has some side effects. Basically, it would get a lot more noise, what's called ripple. So there's ways of controlling that ripple, but one of the disadvantages of a switch mode power supply, even though it's more efficient, is that it has this ripple characteristic. And there's ways of designing around it, but you can't always control it perfectly, and we're going to examine that on the oscilloscope and see a little bit of the difference between a linear regulator and a switch mode power supply and when you might want to use one over the other. We're going to start out with a relatively simple switch mode power supply. The simplest way you can do it is with a single MOSFET and a diode. And we're going to bump this up. We're going to get a little bit more complex, and we're going to drive two MOSFETs switching, opposing each other, and we'll have a special controller chip that does all that for us. So that's the next video. Check it out.